Hey folks. Okay. I'm Vikas. I'm Vikas Sharma. I'm part of the CRED for almost a year. I'm part of the data platform team, and we're building promotion stack also in CRED. My topic for this talk would be using Aerospike for doing efficient stream joins. So I'll take you to the agenda a bit. So to set the context, we'll go through the promotion stack, what it looks like, uh, what were the problems at before we did this, what we did to solve this, what possible approaches we sort of discussed, what we landed as a solution, how we refined it, and we'll talk about a bit more how stream processing at CRED looks like and overall, and some of the future scope. And yeah, so that's the agenda for this talk. So let me take you through the promotion stack. So the promotion stack is built to serve most relevant content to the user. So it is basically a platform that integrates with multiple LOBs. So if you use CRED, we use rewards at CRED, jackpots and everything. Those are primarily powered through promotion stack. So that we handle a lot of relevancy for that. So what it does is, like, whenever the app page loads, it calls the LOB for the farm load. It calls promotion stack to get the most relevant information. Promotions serve the content which is served back to the app. When the user interacts with other content, we gather all this information as user analytical events that flows through our ingestion platform, which basically dumps it to a data lake where we had batch jobs, which would basically get the most insight of what content has been served, like the performance of the content and everything. So let's talk a bit about the user analytical events. So these events basically gives us the feedback about how a content is performing, right? So a few of the metrics that we measure are impression clicks, CTR, which is clicks by impression. So these signals are basically act as a feedback to our system to basically tune our relevancy scores to get the most out for the user. So the problem that we had was, is it, hello, fine, works? Yeah, okay. Uh, do you guys want me to go back to the previous slide if the content was, sure, cool. So yeah, what the problem with that was that the feedback that we were generating to our systems, they were basically batch in nature. So they had an inherent delay of batch processing up to an hour or so. Because of that, what we were not able to do was do a budget cap, frequency cap, updating relevancy score in real time, and not able to do any real-time analytics on top of it. So those were the problem statements that we were working with, and we wanted to improve on it. So we thought that what we can do to do that. So then we thought that let's complement our batch jobs with streaming jobs. With streaming jobs, what we wanted to do was to do the same thing that the batch job is doing, basically doing the joins of event streams, but in a real-time fashion. And that's why we needed stream joins. So why needed stream joins? So the nature of user analytical events or tracking events is that they can't be very heavy in payloads. So they have to be lightweight. And most of the context around what is being served to the user is captured in serving logs. So we had to marry the user signals or the user events with the serving context to get the performance or the feedback signals for a particular content that is served. So yeah, that was the that was the thing. That was the problem that we were trying to solve. So we'll go to yeah. So as I like going like reiterating the same thing. So we got the events here. We did the batch jobs where we would generate reports in batch as well as the feedback signals were in batch. So we wanted to replace it or actually complement it with a stream job that does the same thing but does in real time, where it powers real-time analytics, pushes to Pinot store, where you can get superset dashboards in real time updated. as well as the feedback signals are much in real time. So what the possible approaches that we discussed before building this? So we are primarily on Flink. So we have a real-time processing platform that is basically built on top of Flink. It manages Flink jobs for us. If people have managed streaming jobs, the deployment, rollback, logging metrics, ownership, and a lot of those problems statement has been solved by the real-time platform. So we basically thought that we will build on top of it only. So that's why one of the options was using native stream joins in Flink. So how Flink does joins is using window operations. So these window operations require a state that is managed by Flink. We have RocksDB, managed state store. Why RocksDB? Because it manages or basically stores the stream context in an off-heap manner. If the data that is being stored is getting more than what the memory is, then it spills to disk. And it has a lot of fault-tolerant mechanism to make sure the state is not lost. What are the limitations that we faced in this approach was that our join window was relatively larger. For some join use cases were 12 hours, for some it was up to 2 days, up to 7 days actually. And so as I mentioned, right, we had multiple streams that we joined. One of the stream was serving events, which basically was a bit heavy payload that we wanted to maintain in if we would have maintained that in the state store, the data set for the 12 hour or 7 days would be crossing around 1 TB of storage. So managing this much of a large storage in native or stream join using window operation could be cumbersome. So Flink restarts, like it will take some time to create save points and all of the thing, as well as the RTP that runs on a heterogeneous cluster. So we would have to provision a spatial cluster with a heavy disk with it, and we have to closely monitor it. So we felt that we could do something better. So the other option was to use a fast upsert store. If people are familiar with, like there are a couple of, I can think of fast upsert stores like Apache Kudu, TIDB. So the approach would say that like we create a single table where the primary key would be the join key, and whenever as the stream comes, it basically upserts the same record. So you get a join that is being supported by the data store. What's the, why would you use that? Like, because there is no bound on the how much larger the window could be. And any of the streams, right? If any of the stream is delayed, it would be handled. What the challenges with it is, like Apache Kudu, for example, does not emit CDC events. So whenever update has happened to a record, you will not get that as an update, like the join has been updated. So that, because with one of the requirements that we had was to enrich these user analytic events with the serving context and then do some real-time analytics, which would have beaten that use case. There are other things like TIDB, but the problem with the TIDB is like it's very thick stack to maintain in production, and we don't have that like in CRED as of now. So, but going to like, do we really need upserts? So why would you need upserts? Because you are because the hunch is that the events can come in any order in any of the streams. But by nature, the event stream that is generating through backend system, which is serving context or serving events, it's most likely to come much earlier than what your user events would come. So there is an inherent pace difference between one stream versus the other stream. And we actually don't need unbounded join windows. That was not the use case that we're looking for. So instead of upsert, can we use this pattern that we have seen in this, the way the stream is structured and designed, to basically improve on what we are trying to do? So we thought that, okay, in batch job also there are two types of joins, right? Where is sort merge join, where you pull basically a partition of data which includes the same number of set of keys and then do join and then publish it. Or there is something called as hash join, which is basically you create a hash table in memory for one of the joins and you do a lookup from the another data set to do the joins. So we thought like, why can't we replicate the same thing in streams? So that's why we basically settled on doing a lookup join, because there is a set pattern in the way the streams are delivered. Uh, Mostly the serving events, which is we used as the lookup, would be indexed in a hash table. The hash table is in the external state, which could be in another data store. And whenever as the tracking events or the user events come, they can do a lookup on the hash table and enrich its context and then flush it forward to the next consumer. So what did we need? So we need a fast store that can do single-digit millisecond updates, reads and writes. Should be reliable with strong consistency. Could be horizontally scaled so that for let's say for any event that might come, like World Cup or something, where we would expect a huge load to sustain for a week or so, or a month. So we can easily add up the, basically scale up our hash table, and which basically also has persistence. So what are the candidates that we looked at? So we use DAX plus DDB in CRED. Elasticache is Redis and Aerospike. So when we looked at, when we basically were doing a comparison between all the three options that we had, we chose Aerospike because for the same amount of workload, data stored and the lookups and writes, the Aerospike was much cheaper. We basically used a hybrid storage for Aerospike, where the data is stored in disk and the key space, which is your index, is stored in memory. So with that even hybrid storage, it was able to deliver some millisecond latencies, but that was with NVMe disk for that. The other thing was that we chose the community edition because we did not require CDC or any shadow devices to recover from a lost state. The reason being is that because most of the events have a retention of 2 days in Kafka. So if we have to build a store, we can actually drain the entire stream from the previous offset and then build the state again. The other thing was that we used GP3 SSDs instead of NVMe because our use case was not of some millisecond, but if it hovers around 2 to 4 milliseconds, it would serve a purpose. So yeah, so then going to how we're going to model this on Aerospike. So we have basically settled on that, yes, one of the stream is going to be indexed. The other streams that are coming late will do a lookup on the Aerospike and do the enrichment or lookup join. So the indexing, right, where the way we serve is like our system, whenever we get a request to a system, like a page load, so we serve almost like 40 content per load, per page, which means that we are basically serving around 6,000 with a 6,000 RPS of content, and where 5x peak are there within a month. The user events that are coming, they are around 2 to 3K RPS, which is the read load, and again the same 5x peak per content. So when we basically were doing like how we can do this, so there are two ways, right, where we can index individual content that is served as a separate key, and then do a lookup on that key, because all the user interaction will happen on the same card for a user. But that turned out to be a very huge cost on the key space, where for a 12-hour duration window, our keys were in average were around 260 million, and at a peak, it might go to 1 billion, which would require 120 GB of RAM to store that key space. So there are options where you can store the key space in disk, but they are not as performant as having that in memory. Also, there is a fan out of 40x. So you're getting a 150 request, but we are writing 6,000 writes on Aerospike. So to optimize that, what we used was Aerospike's map CDT. It's a collection data type in Aerospike. So the way we modeled is like for each request that is served, we store the map of each impression or each content that is served, so and the metadata along with it. So yeah, so it dropped our key space by a factor of 40 because we are only getting 150 RPS of writes instead of 6,000. And that means that only we would need 3 to 5 GB of memory. Write fan out reduced by 40x. So same thing, the request ID and impression ID corresponds to the served request, as well as the impression ID corresponds to the each content served in the each request. So the read again would happen on the cardinality, or the most granular thing is impression ID. So when we can do a lookup on map CDD where you can say that the primary key is request ID and the map key is impression ID. So effectively our request, our our user events when they were coming, they would do a lookup on request cross impression ID. This also saves up on our read memory utilization because we are not fetching the entire 40 impressions payload per request or per tracking event. We are only fetching the relevant metadata that is for a particular impression. So at a very initial performance that we did, we were very easily able to do it 500 to 1000 RPS writes and 5K to 10K reads for a cluster size of 3 nodes for Aerospike. So yeah, so what we did was we modeled our streaming jobs like, so the ingestion platform is where we, it's an event source for all the events generated in the system in CRED. So we get serving events in ingestion job, which writes to Aerospike. And when the user events come, they do a lookup on Aerospike, and enrich events are pushed back again to the ingestion platform, where it could be fanned out to multiple places to as a real-time feedback to the serving systems to optimize the ranking, to Databricks to build faster tables, and to Pinot for real-time analytics. So there were certain things that we needed to solve, which basically that was a very base concept around it, but there are a lot of refinements had to be done around it. Though the refinements were like, how do we handle failures? Because state management, right? You can do a lot of things with that data model, with that implementation, but we have to explicitly solve it for our use case using Aerospike. So one of the challenges were, let's say for some intermittent issue, writes are failing. So how do we do that? So what we did was that let's implement a retry operator in Flink. The challenge with that was that our stream that is coming in is very heavy in throughput, in bytes per second, right? Uncompressed, reaching around 200 Mbps or 400 Mbps at perf. And to do a retry state management in the Flink, we have to do a key by operation. Because most of these operations are keyed operations, and that would incur a shuffle in stream. That was basically incurring a huge network activity, which was limiting the throughput that we could get from the service. And it was bottlenecking much before the Aerospike writes could bottleneck. So what we did was that we decoupled this problem, where we created a DLQ pipeline, where if the writes have failed, from the main pipeline it goes to a DLQ topic, where there is a retry job, which basically implements the same retry operator. But because this is going to be a fraction of what the original traffic would be, so this scaled for us. So now we have writes, failure on Aerospike writes are handled through DLQ and retry. So that thing was solved. What next? Yeah, same thing, right? So you have the main pipeline, which is ingestion job. If any failure happens for around 1 to 2%, it goes to DLQ topic, where we do same Flink retry operator, and then it goes to retry topic, it's consumed in ingestion job again, and then retry. So the retry job has a counter which is updates every time, and it does a retry after every 10 seconds. So basically it stores the event within the state for 10 minutes, and it does a retry for 5 times, so 50 minutes of retry interval we have. So it gives a breathing space for Aerospike write latencies to drop down. Yeah. So now there are other thing is like, let's say the writes are not getting issues, but for some reason the serving system or serving events that are coming in that are indexed are delayed by some XY reason, maybe the pipeline broke or something like that. So the events that are coming in which are doing a lookup, how do we handle them, right? So same thing, right, where we implemented a retry operator here also. This is scaled because the size of a tracking event or user event is much smaller, 500 bytes or something, and that was easily we were able to maintain in Flink's state store. Yeah. The other thing that we were facing was that because we are writing a very big payload, right? For each request, we are writing a map of 40 impressions, or it can go up to 60 or 80, depending on the configuration. So the payload size was getting quite huge. And our disk usage was growing very much because we are offloading all of the state to the disk of Aerospike. So what we did was a simpler solve for it was we implemented a compression on the before writing to the Aerospike. So for the same request ID, impression ID, we write a compressed metadata along with the compression type. So whenever the user event comes, the stream processing pipeline picks up this record. It checks for the compression type, what is being compressed with, use the same compression type to decompress and move forward. The other thing that we also implemented here was that we had to basically fire some third-party tracker URLs for some use case. So the third-party tracker URL has its own intrinsic latencies adding to the pipeline. So what we used, so how we solved it was using an async IO operator from Flink itself. It basically does the same thing as any other async IO operation, but it is managed by Flink. So you can set the concurrency and the timeouts and everything to do that. So this is a depiction of how the async IO works for Flink. You can replace database with any external system call. Yeah, so this mostly been what we did for this optimization. The next state is that we do extensive performance test on it, and we carve out a framework for a join operation using states, external states, and contribute back to our real-time platform. The other part was that, so right now we are handling any delays in stream itself, it retries. But what happens if the entire stream state is destroyed? So to recover from that, either we can restart the streams from the very beginning, but it will take time for it to come to the latest offset and generate real-time results. So what we want to do is we want to build a batch reconciliation which will accompany all these stream joins and bake into the RTP itself, where any loss of join that is happening, the processing happening, can be recovered through a batch job and let the real-time pipeline start from where they have, from the latest offset, so that we can start getting real-time signals. As we talked about, right, where our payload size is increasing a lot. So we basically solved it by compression, but we can actually use any columnar store like ScyllaDB or something to basically break down the records into multiple columns, and then the record size will not be a concern for us. And what we can then do is that we can use those columnar store as a state store to do any kind of a join, which could be mandatory also, where either of these streams could be delayed. So basically it's going to act as like a fast upsert store also. Yeah, mostly that what I had to cover. Going bit into what we have as a streams platform at CRED. So we have stream event source stream systems like EventI and US and ingestion. EventI is our service-to-service platform, which is basically which manages service-to-service communication through EventI Kafka bus. So like service 1 and service 2 has an SDK that pushes to Kafka. Then we have fan out consumers that can have some business logic around filtering and stuff, and then we can fan it out to either of like SQS, Kafka, or an HTTP API. So this has helped to scale our event-driven architecture for some of the problem statements. The other part is like we talked about the ingestion platform. So we built ingestion platform was to get the real-time updates from the user. But one thing that we realized was that the load on ingestion service is very varied. It goes up to 10x for any offer that has been on the system. And our Kafka system is not flexible to scale up and scale down. To solve that, what we did was that we introduced a disk buffering within the edge service, where it's written in Go. So we use a library where it's the event stream that is coming in into via an HTTP API. It is cached into the memory, which is disk backed, and at a constant rate, at a determined rate, it flushes to ingestion Kafka. So any 10x peak would flush into the disk, and then with a constant rate, we'll start pushing data to ingestion Kafka so that the Kafka cluster is maintained. And yeah. So yeah, we are hiring rockstar platform engineers. There's a QR code. You can go to the job portal and apply there. And there are the emails and the link to it. Any questions on this? Yeah. Yeah.
Hello.
Hi.
Hi. So, good talk, first of all.
Do you want me to go back to slide?
Yes.
Which one?
The one where you discuss the solution that you proposed, right, before
Yeah.
coming to Aerospike.
Yeah, yeah.
One question I have is, why didn't you guys look at databases as queues? So I think you touched upon ScyllaDB, right?
Yeah, yeah.
It's a columnar store. Why not to build everything on ScyllaDB?
That's what the future is.
Okay.
Right,
Okay,
because we don't have that ScyllaDB as a operational store in. So we were working with what candidates we had, but the future scope is that so Flipkart does a similar thing, right? Where their stream platform system is based on HBase, because at the time that was built, the Spark structure streaming didn't have a very good state management with fault tolerance, so they offloaded all the join operations or window operations to HBase. So with HBase, they were having a lot of difficulty because HBase becomes it's a moody because of JVM and stop double things. So they would only onboard very low throughput join and window operations on top of it. But if you go to ScyllaDB, I think those limitations will not be there, and we can actually offload a lot of state to ScyllaDB kind of a store. Where
because you get CDC out of the box.
There are a lot of so that's what we want to do.
Yeah.
So the real-time platform that we have, so it is built in layers. So there is a core execution layer. I'll go back to that. Yeah. So it's a little dated. Just here, what I'm saying is like we have execution environment. It could be EMR, EKS. But theoretically Databricks also, or any batch job also. Then we have execution modules, which is basically are going to run your pipeline. So it's a Flink pipeline will run in the Flink cluster. It's a Spark pipeline, it's a Spark cluster. And then we have layer one, which is your DSL, domain specific language. So in RTP, we do have our DSL, where we offer small operations as domain specific language like filter and lookup, like filter and transformation. So what we want to do is that we want to bake all of this back to RTP so that the joins are much more universally accessible with a low code. So that's what the future would look like.
Correct. One more question. So in this diagram only, right, you have shown that you have ingestion service and then you have written a Go module which writes to the disk. Doesn't it make it stateful?
It is stateful, yeah.
But then like your pod goes down, how do you manage? Because services generally.
So what happens so the way we have implemented is that if my ingestion rate is as equal to my output rate, then nothing is written to disk. So it is a back pressure managed disk. So
but this service, I'm assuming this is deployed on some VM. Is it a VM?
It's a Kubernetes pod.
So then Kubernetes by design. So you are using stateful pods, or
we are using stateful pods.
Okay, got it.
So the thing is that we are playing on the chances of what might go wrong, right? So if I get a spike, I might not be able to write to cluster and might destabilize it because writes are much high on it, and my consumers will get affected. So what is the next solve to it? Like limit it, right? Safeguard your cluster because that particular infrastructure is not elastic in nature. So if we get a peak, which is, let's say I'm able to write at 40,000 RPS to my cluster and I get a peak of 80K. So the remaining 40K is flushed to the disk and for that duration. And if the disk is, and so we have certain measures in place where we scale up and scale down based on what the ingestion rate is, so that we can have more number of nodes in the ingestion service, which can basically handle that much of extra data into the disk and then flush it out. If for something, if the pod goes down, there are data loss for sure. But because these are analytical events, so 100% data guarantee is not available. We will provide 99.9%, 0.1% being in any disaster scenario where the pods are being terminated because without flushing out the data.
Got it. One last question.
Yeah.
So, are you guys also doing frequency capping somewhere?
We build, yeah.
So which store are you using for that?
So we are basically experimenting some things, but it's something that's not production ready, so not able to comment on it.
Got it. Okay. Thank you.
Okay. Yeah, here.
I want to ask, when you use the DLQ and you use one port to consume it from DLQ and wait for 10 minutes, it will wait till 50 minutes, right? For 5 retries.
Yeah.
So where the data is staying for that 50 minutes? On retry job component only.
Yeah, so retry job, so as I said, right, Flink offers state management on top of RocksDB, which is in memory, and if it spills, it goes to a cluster's disk. So it manages that into that state itself. So Flink stream will have a state, the data would be residing there. There would be a timer that will go out of after 10 minutes, and the same payload will be triggered after 10 minutes.
So data will not remain in this retry job.
It will stay in the retry job.
So if this node goes down somewhere, you will lose the data.
Yeah, so Flink state is fault tolerant that way. So so it does frequently checkpointing of all the operators, where whatever the state of an operator is, it flushed down to the disk. And you can do a manual save point also, where you can specifically ask to create a save point if you are doing a redeployment or something like that. So the state is fault tolerant, it is good, but our use case was that it's a very large join window. So managing that large state in internal Flink state management will be tricky. So that's why we offloaded that part only into external state, which is Aerospike. And idempotency, retries, all of that still remains in the Flink state operator.
Sure.
So you mentioned about batch reconciliation.
Yeah,
Right?
yeah.
Can you go to that slide?
That is one thing that we want to do. I don't have a slide for it,
So
but
I
yeah.
I just wanted to understand. You said you would do that if the entire state is wiped out, right?
Let me correct myself. Not the entire state wiped out, but yeah, could be state wiped out, like the Aerospike cluster goes down completely.
So you are not talking about the Flink state, right?
Not the Flink state.
Okay,
yeah.
yeah, got it.
Well, even that also. Even the Flink state goes down. Like everything, everything is down.
So regarding Flink state, you could just have regular save points and you could minimize the probability of having
That is true, but that would be done for retry and idempotency use cases. But because my join window is in external store, right? And
Right.
so that state store I have to manage. So if let's say the entire cluster goes down, the state is stored, and this is a community edition cluster, so we don't have CDC and shadow devices where we can restore it. So the other way that we have solved is that we basically flush the entire 2 days data from the streaming job back to the cluster. And once the state has been at the place where it should be, we start doing stream joins again. But that will take time, right? And so that is a intermittent solve, right? Where you have something to do, but it's not the best. So and because it will delay your real-time feedbacks by the time it is taking to manage the setup, right? So the batch reconciliation will come in places like, because all of this data is already published to data lake. Right. So we have all of this data into data lake. So we can write batch jobs which can do the join for that period that is lost, and then again publish it to Kafka in a fashion.
Got it.
Yeah.
Got it. Thank you.
Any questions? Yeah.
Since it was mentioned that Flink is deployed on top of EMR here, so how do you manage the auto scaling there?
Or that we have built.
That you have self-built. Okay,
Yeah.
it's not. Okay.
That's what the platform does for you.
Okay.
So it manages. It basically gives you Flink management as a service, right? So it also has its own operators where you can use to write or define a pipeline using some config, or you can have your custom jobs. So these are custom jobs that are running on top of RTP, and RTP manages scaling for me. It manages. So there are 2 levels of scaling, right? Where you can set a scaling for your EMR cluster. If they're required, the EMR will add more nodes, and so that was it does. So, but automatically Flink, the cluster will not add pods. You have to restart your job with some parallelism, and then add more slots if you want. But it will spin up the task managers by itself.
Got it. Okay.
Thank you, guys.